Okay, so now we're going to talk about the remainder theorem, which is a very useful result in maths. It is a result that you can and should understand. Before we do that, we're actually going to do an example and see what it actually tells us and how we use it. If you can understand the remainder theorem, you'll understand the factor theorem, which comes in a second. This result completely relies on understanding how algebraic long division works. So what it says is if you want to do a division, if you're going to divide some big polynomial here by a linear expression, which is what we've been doing up to now, this tells you what the remainder is without you needing to do the division. Now it doesn't tell you the answer, so to speak, it doesn't tell you how many times this goes into this, but it is a shortcut to getting the remainder, which is often all we need. So what are we actually doing here? It's saying if you've got an expression, the thing which is being divided, and you're dividing it by something like this, I'm saying you need to plug a certain number into this. The thing you want to divide, if you plug a certain number into it, it will give you the remainder when you divide by this thing here. Now, the thing you divide in is what makes the divisor 0. That maybe overcomplicates it, but we'll see in a second what I mean by that. All we're saying is if you're dividing by something, you think what would make that thing you're dividing by 0, plug that into the original expression, and you will get the remainder as your answer without doing long division. So let's see that in action here. So here we're being asked to divide this thing here. This is filling the role of fx here, okay? And it's being divided by x minus 3. That's the linear thing we're dividing by. So what I'm saying is, look at x minus 3 and decide what makes that 0. What value of x makes that 0? A little bit of perhaps unnecessary rough work here, and we see that x is 3. So if I found the value which makes this bracket 0, and I plug it into this, I will get the remainder that I would get if I did the long division. So 3 makes this 0, I plug it into this thing here, and you end up getting an answer of 2. So what this says is if you did x minus 3 divided into this, you would do a lot of working out, you would get how many times it goes in, but this is the remainder that you would get. Okay? So it would be a good thing to check this. I would suggest you go away and do the algebraic long division, divide this into this, and check that you get 2. Your algebraic long division will take you longer than what I've just done, but it will have the benefit of giving you the actually how many times it goes in. It will give you the quotient. So let's see why this is the case, and I do think this is worth understanding. So let's look at this specific example first, and then we'll go back to the more algebraic version. So if I start with this and I do 2x squared minus 5x minus 1, and I divide it by x minus 3, perhaps you've just done this, you will get the quotient. You will find out how many times it goes in. Let me call that q of x. Okay, there'll be some kind of piece of algebra there, the thing we used to put in brackets. And there will be a remainder, okay? And what you would do is you would write that remainder over the thing you're initially dividing by. You have an answer that looks a bit like that. Now, if I times through by x minus 3, I will get this statement here. I will get that 2x squared minus 5x minus 1 equals qx times x minus 3 plus r. So when you times through by this, it disappears on this side. When you times this term by x minus 3, it picks up that factor x minus 3. And when you times this by x minus 3, it just becomes r. Now, if you're interested in finding this remainder, you want all this stuff to disappear. So you don't really know anything about qx, but you do know how to make x minus 3 disappear. If you plug in 3, then this bit will disappear. You'll get the remainder by itself, and if you plug 3 into that, you have the remainder. This is exactly the same thing that we've done up here. We've looked at what makes x minus 3 0, what makes the thing you're dividing through by 0, we've plugged it into the thing you are dividing by, and it gives me the remainder. Let me just do that again in more algebraic terms. So, if we look at this statement up here, I'm saying that when you divide f of x by ax minus b, then you will get an answer I don't know at the moment. You'll get some kind of chunk of algebra, how many times the ax minus b goes into fx, and you will also get a remainder, which you will write over the initial divisor. Now, timesing through by ax minus b gives you f of x equals q of x times ax minus b plus r. You are trying to get access to this number here. You want to know what the remainder is. So we want pretty much everything else to disappear. We certainly want this awkward bit here to go away. We don't know how to make qx disappear, but we know how to make ax minus b disappear. If you plug in the number that makes this disappear, this will disappear. So what makes this thing here go away? Well, when does ax minus b equal 0? Well, rearranging this, it happens when x equals b over a. So if you plug in the value x equals b over a into this whole thing, you will get f of b over a equals, now this bit will disappear because you've picked a value of x that makes this whole thing disappear, but the remainder will be left by itself, and you will get r. So exactly like the statement above, we're saying that the remainder, when you divide by this thing here, is f of b over a. You won't be asked to prove that, but I think that understanding can be particularly useful sometimes in some kinds of questions to know why the remainder theorem works. Now, operationally, this tends to go quite badly wrong, and the reason is that people aren't very clear on what value they should be plugging in. If you learn this thing off, this is all very well, but let me just test by doing a few extra examples what the value you would plug in is. That's the key thing. If you're dividing by x minus b, I'm saying plug in b over a. Here, I said if you're dividing by x minus 3, plug in 3. If I was dividing by x plus 4, the number I would plug in is minus 4. That's what makes this 0. If I was dividing in something like 7x minus 3, the number I plug in is 3 over 7. That's what makes this thing disappear. Okay? If I was dividing by, 3x plus 2, then the number I plug in is minus 2 over 3. You can either do this by setting up these mini little statements like I've done down here, or you can go back to this thing here. It's the negative value of whatever b is, so the negative value of minus 3 is 3, negative value of 2 is minus 2, divided by what's in front of the x. I honestly think rather than maybe learning off that thing there, I would just look at what you're divided by and say what value of x makes it 0. So let's move on to the next example and apply all of that. So here, as we've already discussed, the first thing to decide is, well, I'm dividing this by something. What's the value I'm going to be plugging in? I only want the remainder, so I'm not doing full long division. So I'm dividing this into this. So I'll maybe call the thing I'm being divided through by fx to match the statement of the theorem at the beginning. But the key thing here is to find the value. What makes this 0? You can maybe see straight away, maybe you do some rough work, but what makes this 0 is x being minus a half. So that's the value I plug into this. So I take my minus a half, plug into this thing here, so that'll give me minus a half cubed, plus 2 lots of minus a half squared, minus 7 lots of minus a half, minus 12. And I get my final answer, minus 65 over 8. That's the final number that you would end up with at the end if you did do the division and divided 2x plus 1 into this thing here. That's a particularly difficult one to do because if you divide 2x into x cubed, you're going to get it going in a half times, well, a half x squared times. So this remainder theorem is a much quicker way of digging out the remainder if that's all you're interested in. Okay, another example. Down here, you've been given a polynomial. Okay, it's got an unknown in it, an unknown a in it, but it's being divided by x plus 1. Because there's something unknown in part of the question, that's why you're being given the final answer. You're being told that the remainder is 12. So let's use the remainder theorem. I know that when I divide this into this, I get a remainder of 12. So what is it that makes this 0? It's minus 1. So if you plug minus 1 into this, the remainder comes out, which is 12. So let's do that. Let's plug minus 1 into this and know that the answer, the value I should get out, is the remainder, which is 12. So plugging minus 1 into this, I get this expression here, and that's equal to 12, so I end up simplifying that down to get a equals 2. This is just a different version of the remainder theorem, okay? It's the kind of classic flip of a question. Rather than giving you all the information you need for the question to work out the remainder, we're giving you the remainder and taking part of the information out of the question. Here's another example similar to what you've just done. You're being given a polynomial with some missing information in it, well, missing an a just, and you're being told that you are dividing by x plus 2 and you're also dividing by x minus 1, and although you don't know the remainders, you know a relationship between them. It is a question about the remainders, okay? So let's work out what the remainder is when I divide by x plus 2. I won't be able to get rid of this a, so it will still be a piece of algebra. So if you want to divide by x plus 2 and find the remainder, you're saying what makes x plus 2 0? It's a value of x minus 2. So let's plug minus 2 into this thing here. So when you plug minus 2 into this, you work through and you get this expression here. Okay? So this is the remainder when you divide by x plus 2. And that's a fact which is part of this question, so we'll just leave that there for a second. I'm also interested in the remainder when I divide by x minus 1. What makes x minus 1 0? Well, it's when x is 1. So let's plug in 1 and we get this remainder here. So we're interested in the relationship between this remainder and this remainder. This is the remainder when you divide by x plus 2, and this is the remainder when you divide by x minus 1. Let's read the question very carefully to see how they're related. So it says, the remainder when you divide by x plus 2, this thing here, is 8 times this remainder here. This is 8 times this one here. So I set this up like this, being very careful which side the 8 goes on, and I just work through from there, and I do get my final answer of a equals 2. You could go back and check this by all means. Go back and actually divide x plus 2 into 2x to the 4 plus 3x squared minus x plus 2. See what remainder you get. You could then divide x minus 1 into 2x to the 4 plus 3x squared minus x plus 2, and the remainders you get should be related by a factor of 8. So let's move further down. Yeah, okay, so I'm still recording. You heard my silent moments there. So we're now onto the factor theorem. Now this is nothing different. This is just a specific case of the remainder theorem. The remainder theorem lets you work out what the remainder is. If something is a factor, if you're going to divide by something like this thing here and it's a factor, it will give a remainder of 0. Okay. Now this is actually more usefully used in reverse. Okay. So I'm sort of saying if you can find a value, which when you plug it in gives you 0, then you could probably trace back and work out what that remainder is. So if I give you a big polynomial and say that when you plug in the value 1, you get a remainder of 0, that's telling you that there must be a factor involved. There must be something which goes in exactly. And thinking back to what we did earlier on, it's really the reverse of that. If 1 is going to make it 0, then the factor must be x minus 1. So that's all a bit kind of, I don't know, vague. So let's have a look at this in action. So let's move up a bit. So, first thing, it says, show that x minus 1 is a factor of this. Oh, hang on, well, that's a really good starting point. So, if I'm showing this is a factor, well, I'm expecting that if I calculate the remainder of this thing, it should be 0. There should be no remainder because it's a factor. So, rather than actually doing the long division, what I'm going to say is, initially at least, I'm going to say, well, let's just check that when I plug in 1, the number which makes it 0, do I get out 0? So, if I put in 1 to this thing here, you get a remainder of 0. A remainder of 0 is telling you that this thing is a factor. Now, because of the follow-up part of this question, I am going to actually have to do the division. It says, hence, factorise this thing here. So I've already found one factor. I found that x minus 1 is a factor. So if it's a factor, let's divide it in. Now, the reason I'm dividing this in is not because I'm interested in this remainder. I know that remainder will be 0 because this is a factor. It's this thing I want to work out. I want to see how many times x minus 1 goes in. I know it goes in exactly, but I don't know how many times. So by this point, you're probably quite comfortable with long division, so I'll leave out that part there. But once I get down to here, I've learnt something. I've learnt that when you do x cubed plus 2x squared minus x minus 2 divided by x minus 1, I know that the answer is x squared plus 3x plus 2 plus nothing. There's no remainder on the end. Now, I'm interested in this thing here, so I'm just writing it slightly differently. I'm going to multiply through by x minus 1. I know that my polynomial I'm interested in, this thing here, is equal to x minus 1 times this. Just timesing both sides of this by x minus 1. Now that's already the beginning of a factorization, but I should then always look at this quadratic and see if I can factorize it. Now, it might be the case that at this point you've stopped. Maybe the quadratic doesn't factorize, okay? And that would be fully factorized at that point, okay? But in this case, we can clearly see that this does factorize, and this is my final factorization. This is quite a classic format of question. I find a factor or check something is a factor, divide it in to see how many times that factor goes in, and then factorize that remaining bit. So this is perhaps the most useful application that we're going to have now of all of the stuff we've done with the remainder, factor theorem, and algebraic long division, and that is factorizing a cubic. Okay? This question here is not so dissimilar to the previous example, it's just you're not giving any help. In the previous one, you were told a linear factor, and then we divided it in and carried on and fully factorized. Here, you're told nothing at all. It's up to you to find a linear factor. And the way we do that is to try and find that linear factor by trial and error. We're going to plug numbers into this until we find a number that gives us 0. Okay? If you get a remainder of 0, you know you've found a factor. Okay? And we know we can find remainders by plugging numbers in. So, first things first is I'm going to go through these numbers logically. So I'm going to try 1, then minus 1, then 2, then minus 2, 3, then minus 3, 4, then minus 4. I'm going to move away from 0 in the positive and the negative direction at the same time. I wouldn't suggest you try 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then start the negative numbers. I think it's better to work your way out logically. So in this case, I've tried plugging f of 1 in, okay? Now, there we go. The linear factor which 1 makes 0 is this thing here, okay? So I'm saying this expression here, this working out here, is finding out what the remainder is when you divide by x minus 1, okay? If I had asked you separately, what do you get when you divide by x minus 1, you would have plugged in 1 and you'll get a number, okay? I didn't actually work out what that number was. That number is minus 48. Okay, so if you divide this expression here by x minus 1, this working out tells me that you get a remainder of minus 48. Well, good to know, but that's not helping me to find a factor. If I plug in here minus 1, then really I'm trying to work out what the remainder is when I divide by x plus 1. Okay. When I do that, I didn't bother working out here because it wasn't particularly interesting to me. I got an answer of plus 48. Okay, so when you divide this by this, you get a remainder of 48. I'm so interested I didn't even work out that 48. That is not a factor, I'm not interested in it. And so on until I get to this, finally this interesting value. When I put in minus 2, which is really me experimenting with division by x plus 2, so if I divide x plus 2 into this, I get a remainder of 0, meaning that x plus 2 is a factor. That is a very important set of work there. Now, you might not be very comfortable with my way of saying, well, if you're trying 1, then you're experimenting with this particular factor here. If you don't like that idea of what makes this 0, then by all means just learn the standard definition of the remainder theorem. It does tell you, and so does the factor theorem, that if plugging in a particular value gives you 0, then it tells you how to translate it back into what that factor must have been. So this will come with a bit more practice. We'll do another example in a second. I'll maybe throw a few extra examples in, but for now, you need to be aware that a question like that begins with trial and error until you find a number that makes it 0. What that actually tells you about what the factor is the difficult bit. But here, trust me that we know that x plus 2 is a factor. So I'm going to divide x plus 2 in to see how many times it goes, and it goes in this number of times. I followed this all the way through because it's nice to get the 0 at the end. You trust this a lot more if you've got that x plus 2 gives a remainder of 0, because that's what we're basing the whole working out on. So at this point, I know that when you divide this by this, you get this. So I have really factorized this expression here. It's equal to x plus 2 times this. I mean, I'll put in that in between step. We all would be happy knowing that 2x cubed minus 12x squared minus 2x plus 60 over x plus 2 equals 2x squared minus 16x plus 30. All I've done in writing this thing here is I've times through by x plus 2. So I've got this by itself by bringing this x plus 2 across. So the original statement, the thing we're interested in, is equal to x plus 2, one of the factors, times by this. That's how many times x plus 2 goes in. So my next step is to fully factorize. I want to factorize this. Before I go any further, I notice that 2 comes outside, which makes factorization a lot easier. So 2 comes outside. I'm looking at this thing here, and I factorize it to give me this thing here. Okay. If you didn't bring the 2 outside, you need to be careful at the end when you find your 2 factors here that you take the factor of 2 out that will definitely appear in one of them, because this says fully factorized. So it's 2 times x plus 2 times x minus 3 times x minus 5. Now, the next example is not so dissimilar, but this idea of factorizing cubics involves trial and error to begin with, finding a number that gives you 0, and understanding the factor theorem well enough to know what factor that is that gives you 0. So I might even now, before we go any further, just try a few more examples. So if, for instance, I found that f of 3 gave me 0, I was doing some trial and error, that tells me immediately that x minus 3 is a factor. If I found that f of minus 17 was 0, that tells me that x plus 17 is a factor. If I found, a bit more difficult, if I found f of a half was 0, then that would tell me that 2x minus 1 is a factor. Now, either because you've learnt off the factor theorem, or just look at what I've written down now, that is a piece of maths which a half makes 0. Okay, so that's the piece of maths which when you plug a half in gives you 0. That's the piece of maths which when you plug in minus 17 gives you 0. That's the piece of maths which when you plug in 3 gives you 0. This here, if you've really learnt off the factor theorem, comes from you knowing that if f of b over a is 0, then that means the factor is ax minus b. Yep, that's right. So let's move on. Let's now move down and look at this example here, which is just one extra step to it. Okay. Now, this thing is saying find the solutions to a cubic. If you asked to find the solutions to a quadratic, you would be thinking factorization probably first of all, and then maybe the quadratic formula. If you're trying to solve a cubic, the cubic formula is horrific. I mean, look it up at some time. It's not an easy thing to use. So I've rearranged this to get a 0, which is always the first step in any equation solving. But once I get to this point here, I'm hoping to be able to factorize this, and that will be the method you will use in C1. So I want to factorize this. So now it becomes exactly the same as the previous question. At the end, I'll just remember that I'm not just factorizing, I'm factorizing so I can solve. So to factorize this, I'm going to do some trial and error again. So I'm going to start trying numbers. I've tried 1, and 1 has given me an answer here of -3, so there's no factors involved in that. I'm not getting that magic value of 0. When I try -1, again, I get some kind of number here. I get -3. That's not 0. That's not giving me a factor. When I try 2, however, though, I do get 0. I know that I found a factor here. Just be very careful that if 2 is giving you an answer of 0, then the factor is x minus 2. Either because you're applying the statement of the factor theorem very carefully with all the a's and the b's, or because you've thought about this and said, well, what piece of maths becomes 0 when you plug in 2? And it's this. That seems a bit more hand-wavy, that, but for me, that what gives you 0 way of doing things is really appealing back to what the factor and remainder theorem are really saying. But by either method, I've got a linear factor. That's the first step in this. Okay, so once I've got my linear factor, I'm going to divide it in to see how many times it goes. So I'm dividing x minus 2 into this. I work through and I get no remainder as I'd expect, but I get this as how many times it goes in. So just making that point really clear, you know that x cubed minus x squared minus x minus 2 divided by x minus 2 gives you x squared plus x plus 1. If you multiply through by this, then we jump straight away to what I've written down here. Okay. So at this point here, we're hoping to factorize as far as possible. So you look at this thing here and you say, right, let's try and factorize that. Pretty quickly you realize it doesn't factorize. So, okay, it's not going to be that nice to solve. Here's the bit to be really, really careful with. Okay, so this doesn't factorize, so you're not going to get a nice statement of 3 answers. You're not going to say this bracket is 0, this bracket is 0, or this bracket is 0. This is stuck staying like this. It doesn't factorize. Don't assume that because something doesn't factorize, it doesn't have solutions. You've seen many quadratics in your time which don't factorize, but the quadratic formula does give an answer. Okay, so in solving this, I am still going to say, when is this 0? Well, this is 0 when x, that's not very clear, when x equals 2. Or, alternatively, I could be looking at when is this 0? When is x squared plus x plus 1 equal to 0? Now, I couldn't factorize that, but it might still have a solution. If you go and use the quadratic formula, or even have a suspicion, first of all, that it's not going to solve, when you work out b squared minus 4ac, you're going to get 1 minus 4ac, you're going to get minus 3, which is less than 0. The quadratic formula doesn't give an answer. Okay, if something doesn't factorize, that doesn't tell you there aren't any answers, but if the quadratic formula fails, there are definitely no answers. So, you fully factorized it, this bracket gave you an answer, this bracket gave you no answers. Don't assume that cubics always have 3 answers, in this case you've only got 1. Really, I should probably call it a day there, but I'm going to keep going because there's nice stuff to be said. So, if I was to draw a graph of this, if I found solutions of this thing here, I've really been finding the roots of this thing here. And I've found out here that there's only one root, which happens x equals 2. People get a bit confused about how you could draw a cubic which has only got one answer, but it's very, very possible. So here, that's my only answer. To get a sense of kind of scale, I know that minus 2 is my y-intercept. Now, this is the only time that I'm allowed to touch the axis, okay? Now, if that's the only time I'm allowed to touch the axis, I'm already below the axis here. This is the point where I cross. So I'm going to go across the axis like that, and it must do something like that. Of all the cubics you can draw, a cubic must always cross the axis at least once. But you have the choice of where you position it. You can position it other places where you do get 3, but there is a way of positioning a cubic, particularly a kind of a going up cubic, because it's got a positive x cubed. There is a way of positioning those so that it only crosses once. Again, before we even go any further, that drawing idea is important. I mean, you can never avoid crossing the x-axis once, okay? You might actually end up crossing it twice, and you might actually get that kind of classic case where you do it 3 times, but you're guaranteed to do it once, which tells you that a cubic is guaranteed to have at least one answer. So you're guaranteed to be able to get at least one answer out when you solve a cubic. Okay, so now some kind of general questions to really test our understanding of this. So here we're being given a polynomial, and in this polynomial there are two unknowns. So hopefully we're going to be given two pieces of information here. So here we're being told that it has factors x minus 1 and x plus 3. Now, straight away you should be thinking, what does the factor theorem then tell me? That tells me if I plug in 1, not minus 1, if I plug in 1, this should give me 0. If I plug in minus 3, this should give me 0. Minus 3, because minus 3 is what makes this 0. So, when I plug in 1, I should get 0. So let's plug in 1 to this thing here, and we get an answer of 0. I rearrange that then to get a and b on one side and the number on the other. Okay, x plus 3 is a factor, so when you plug in minus 3, you get 0. So plugging minus 3 into this thing here, you have this piece of algebra here equal to 0, rearrange it to get a number on one side and the a's and b's on the other, and then I go through and I solve simultaneously. Okay, these are simultaneous equations in two unknowns, so I go through to that point there, and I find out that a is 3 and b is minus 19. Okay, so this thing here is no longer mysterious. So the next bit's more interesting. It says you find a and b, lovely, and find the third factor. So you've already got these two here, and you're trying to find the third of those factors. So let's see what we know. We know that x minus 1 and x plus 3 are both factors. Okay, so that means that x minus 1 times x plus 3 is a factor. If, for instance, 2 divides into a number and 3 divides into a number, then 6 divides into the number. If 5 divides into a number and 11 divides into a number, then 55 divides into that number. So we know that this thing is a factor. So expanding that out, we're really saying that x squared plus 2x minus 3 is a factor of this thing here. And the question is saying, well, how many times does that go in? What is the remaining factor? So let's divide the two factors we know, which are x squared plus 2x minus 3, into the original thing. And don't forget a and b are now known things. So going through all my long division, I do indeed get a 0 at the end because this goes in exactly. And I find out that this goes into this 3x minus 5 times. So this thing is broken up into this times this. 3x cubed plus x squared minus 19x plus 15 is equal to x squared plus 2x minus 3 times 3x minus 5. At this point, I've just broken this back down into the x minus 1 and the x plus 3 that this came from. So I was asked, when does it cross the x-axis? Well, looking at this thing here and saying, when is it 0? It's very obvious that happens when x is 1, x is minus 3, or x is 5 over 3. At that point there, that's the structure of that question done, but it might be worth looking at this because this is a bit of a step up. I mean, here I've actually divided a quadratic into this thing here. So if you look at this here, it doesn't really make much difference, it's just more terms to manage. If I do x squared into 3x cubed, it goes 3x times. So times 3x by this whole thing here, and you get 3x cubed, 6x squared minus 9x. That's 3x times in this whole thing. I draw my line, and there's three things on the go here. All points I'm dealing with three things. Do my takeaway, something disappears. Takeaway. Bring this down, because I'm always trying to keep the same number of terms here as there are there. Carrying it through, I do get my 0. Let's move down a bit more. So, next one. This is a mixture of the remainder and the factor theorem. I'm giving you here a polynomial with an a and a b unknown, so I'm hoping to be told two pieces of information, and I am. I'm being told it's got a remainder of 1 when you divide by this thing here, and I'm being told x plus 2 is a factor. So it has a remainder of 1 when you divide by this thing here. So if you were dividing this into this, the number you'd be plugging in is 1/2, either by looking at what the remainder theorem says or by saying what makes this 0. So if you plug in a half into this thing here, you get the remainder, and I'm being told that that remainder is 1. So when you plug a half into this thing here, you get this, and that should be equal to 1. You rearrange all that to keep the a and the b on one side, the number on the other, and you have this linear equation here. Perhaps the easier one to use is that x plus 2 is a factor. So if you plug minus 2 in, the thing which makes this 0, you get an answer of 0. That's really still the remainder theorem. That's saying when you plug in the minus 2, you get no remainder because it's a factor. You get 0. So plug minus 2 into this, you get this thing equal to 0, rearranging it again to get a and b on one side, the number on the other, and then this should just immediately leap off the page as being simultaneous equations and two unknowns. On autopilot almost you solve, and you get a is 1.3 and b is 0.9. So here we have a nice example which is mainly about the factor theorem, but actually it really does test if you understand your graph transformations as well. So firstly, I'm just going to add on the little piece of information which is told below that this y-intercept happens at 16. Just I couldn't quite draw it properly when I first created the diagram. So at this point here, I've got a diagram, and really it tells me 4 clear pieces of information. It gives me this point that it passes through, this point that passes through, this point, and also this point. Now, it's very easy in this question to ignore what this is telling you. It's very tempting to think that this is enough information to give you the answer, and we'll address that as we go. But one thing to be really clear about is, if you're trying to write down what a cubic is from scratch, then the form of a cubic is ax cubed plus bx squared plus cx plus d. So clearly I'm going to need to use 4 pieces of information to find these 4 unknowns. If you're thinking about a quadratic suggests 2, but you need 3 pieces of information to find a quadratic. I mean, a quadratic is ax squared plus bx plus c. And even just think about a linear graph. It's not enough to know 1 point that a linear passes through. You need to know 2 points for 2 pieces of information. Okay, so going back to this diagram up here, I'm first of all going to just focus on these roots here, but we'll see in a second why that's not quite enough. So I can see that when you plug in 2, you get an answer of 0. Okay, when you plug in 2, you get an answer of 0. When you plug in 1, you get an answer of 0. And when you plug in minus 2, you get an answer of 0. Now, the factor theorem allows me straight away to transfer that into information. If you found that minus 2 gives you 0, then x plus 2 is a factor. If plugging in 1 gives you 0, then x minus 1 is a factor. If plugging in 2 gives you 0, then x minus 2 is a factor. Now, it's very easy, without even thinking about the factor theorem, to jump straight to this point here. If you were going to write down this cubic in a sort of factorized form, as 3 brackets like this, you would be saying, well, if I know that plugging in minus 2 gives me 0, then I want a bracket that makes me get 0 overall when I plug in minus 2. So think of a bracket that would give you 0 when you plug in minus 2. Well, that's a good example of one. If you think about this one here, this f of 1 equals 0, you want a bracket that means when you plug in 1, you do get out 0. So I'm going to go for x minus 1. And finally, for this last one here, you want a bracket which, when you plug in 2, gives you 0. So I'm going to go for x minus 2. So that looks very, very tempting up there. And what I've done down here is do almost the same thing. I said y is equal to x plus 2, x minus 1, and x minus 2. But I've introduced this k value here. Okay? I have to be very, very careful about making sure I do introduce that. Because while this thing up here is perfectly true, it does pass through these points here, it's not necessarily the cubic that's drawn there. For instance, this would be another example of a cubic that passes through those 3 points. This would be another example of a cubic that passes through those 3 points. There are lots of cubics, infinitely many, that pass through 3 given points. It's not enough. Okay? If you look at the shape of these 3 cubics drawn here, the one that was given, the blue one and the red one, you can actually see that they've all been stretched in an up and down direction. They've sort of been fixed points on the x-axis but stretched in the up and down direction. That's the same as multiplying by a number. It's one of the graph transformations you've seen earlier. There's actually an infinity of different options here. Okay? There could be a number in front. Up here, the way we arrived at this was to say that we need an expression such that when you plug in minus 2 you get 0, when you plug in 1 you get 0, and when you plug in 2 you get 0. But of course if you look at this thing here, these things would all still give you a 0 if there was a number in front. There couldn't be anything more than a number. If there was some algebra there, like another x minus 3 term, well that would mean that 3 also gives you 0, there'd be another root. But there could be a number. That number doesn't affect this expression here, giving you 0s at the 3 points you want. So that k must be there. So this number's in front, and how are we going to find it? Well, we use the remaining piece of information. We know that that y-intercept up there must be at 16. So the easy way of doing this is just to plug in the coordinate. So if you plug in that coordinate, you should get a y value of 16 when you plug in 0. So plug in 0, these bits all reduce down to these numbers here. The k is still there, and you find that k is 4, giving you this final answer. The other way of doing this, which is really exactly the same thing, is to say, well, if I look at this thing here, I know the y-intercept has got a value of 16. What would the y-intercept be? Well, when you multiply this out, which I wouldn't recommend doing, when you multiply out, you get loads of x terms. The only way you wouldn't get an x term is when you do the 2 times the minus 1 times the minus 2 times by the k, which is exactly the same thing as what's happened down here. There's a lot going on there, but it's worth thinking about this question. If you were going to just learn it off, you would learn off that the roots give you those 3 factors, and just remember to put in that extra k, that extra factor that could be there. The overall other way of doing this, which really doesn't rely at all on the factor theorem, is to go right back to much earlier on your notes and to think about examples you've maybe done where you were trying to find the equation of a quadratic based on 3 points it passed through. You could, quite time consuming, have this thing here, this is a cubic here. You could plug in that y equals 0 when x is minus 2. Plug all that in. That would give you an equation in A, B, C, and D. You could plug in that when x is 1, you get out y is 0. That would give you a simultaneous equation in A, B, C, and D. If you plugged in this point, this point, and this point, you would get 4 equations, 4 unknowns. You could go ahead and solve that. Now that's a step up from anything you've done because you've only solved equations in 3 unknowns, but it is the same method. All of these methods, though, require 4 points to talk about a cubic. For all that chat of nearly 6 minutes worth of talking now, really it almost comes down to just learning off this little quirk that you need to remember that there might be a number in front of the factors you found.